Hello, folks. All right, so got some feedback on the last lab, and I think we're going to approach this better. And I actually am filming this totally different this time. So we're going to do a little bit of a pre-prep with just on the screen and looking at the lab. And you're going to have access to the lab this time as it would have been handed out to students in class, and then with my answers worked out on it too. So you actually see my final results. And I have some more focused questions compared to last time. All right, so in this lab, we're looking at single and double displacement reactions, and it is just that, single and double displacement. So very much like, well, we got the single displacement down here at the bottom, which is swapping magnesium with aluminum. And then we're going to have some double displacement where we actually have the metals swapping with each other. So on the left, I have lead nitrate. On the right, it's lead chloride. And the sodium ends up with the nitrate. All right. Now, the point of doing all this is in the class, we're introducing some of these, and we point out that, like on the double displacement, we have certain ones that actually form precipitate, and we can predict that in many cases based on our species and what they are. Like lead on this example two there, we would have actually predicted lead 2 chloride precipitated because it's one of our exceptions for the solubility of chloride. All right. Now, knowing that it precipitates and what it looks like when it precipitates are totally different things. So doing this lab and seeing that firsthand is a benefit. All right, the other weird thing we're going to look at on our single replacement reactions is it turns out one direction is always more favorable than the other. What I mean by that, what we can think of is reversing the equation and having aluminum mixed in with magnesium chloride. You might think, well, it should do a single replacement as well and make Mg and then aluminum chloride. And actually, if I balance this out, that should be 3, that should be 2. Therefore, I need 2 of these to every 3 of those, and therefore 3 here and a 2 there. And technically, if you look, the example 1 equation and the one I just wrote are just the complete mirror of one another. Well, we will find there's always a preferred direction. And preferred in this case means if I were to mix these two test tubes, like have magnesium and aluminum chloride, and then have aluminum and magnesium chloride, one of them metal's just going to get wet, and the other one we would actually see a chemical reaction. So it turns out one of those two metals is more reactive than the other. Now, on this lab, we have what we call an activity series. And up here at the top, it says potassium is more active than gold. And matter of fact, we could look at that, and it seems that if we look for aluminum and magnesium, um, they're not really on here. That's because this is not a complete table. It's on purpose incomplete. But that's not what we're not gonna try to make it full. We're not gonna try to do it. We're actually gonna study things that are just on this list. And so we could actually get an idea of how we're supposed to make that call. And that's what we're going to be doing in this lab. We're going to have a section, part 1, part A, where we actually mix a bunch of solutions. That's these 11 test tubes. And then we'll do part 2, where we're just going to react in with different metals with just acid. And then our last part, we're going to do some of those single replacement reactions and see how they compete with each other. Now, what I'm going to do is have 3 separate videos for each one of these parts. We'll have a part here, and we'll have a part here, and we'll have a part down here. And I separated it so we can do each section separately. But before we do that, I wanted to actually go ahead and on that part A with the single and double displacement reactions, we're going to go ahead and complete this table ahead of time. Now, we're not going to be able to do any of the evidence of reaction. We're just going to try to predict our equations based on what we know about our solubility rules. All right, so what I mean by that, let's look at what this first reaction is. It is sodium chloride mixed with silver nitrate. Well, I know the charge of sodium and I know the charge of chloride. So sodium chloride is just NaCl. And then silver nitrate, Ag is positive, NO3 is negative. So AgNO3. All right, I have 2 ionic compounds, 2 metals, 2 nonmetals. This is a double displacement reaction. So I'm going to swap the two. I'll put the silver with the chlorine and then the sodium with the nitrate. I need to write smaller. Fortunately, I'm on fake paper, so I can go right off the page. And matter of fact, why don't I just clean this up right off the bat since I can. So that was AgNO3, and I'm going to make NaNO3 and AgCl. All right, now phases wise, because it is balanced in the sense that I don't need to add coefficients, everything's just a 1. But I do need to specify if I got solid or precipitate or precipitates and then aqueous. Like for instance, we happen to know every single sodium salt, no matter what it's with, is aqueous, so I can put AQ in front of those. And we also know nitrates are also always aqueous. But chlorides with silver would be a precipitate. All right, so when we get to the lab, we're going to be expecting that to form a precipitate. We're expecting it to form a solid when we mix. When we actually fill out our data sheet, we're going to write what that solid actually looks like. Now, it might not be obvious right away. Sometimes we'll want to let that solid settle some, because if it collects on the bottom, it's a little bit easier to make out the color of it. That one, for instance, is going to be a white powder, but we won't know that until we do it in the lab. All right, so that's equation 1, and that's all we want to do ahead of time is get that balanced equation. It makes a good practice. Make sure we understand our solubility rules. All right, so number 2, zinc metal and hydrochloric acid. Hydrochloric acid is HCl aqueous. All right, I have a metal all by itself. I'm mixing it with something. This is the backbone or the basic building blocks of a single replacement reaction. So because it's that, I know the zinc must end up with the chloride, because the zinc is a positive charged ion when it forms an ion, and chlorine is the negative ion. So it's going to be predicted to make ZnCl2. And since it's a chloride and that's not one of the special chlorides that are insoluble, I'm going to go ahead and say it's aqueous. And then the other thing is the H. It's not going to come off as just H because that's atomic hydrogen. It's not going to form ions because I don't need to. It actually forms the molecule all by itself, or H2, which would be a gas. It's kind of interesting. And we suspect that's going to happen many times when we get a single replacement with an acid. We expect hydrogen gas to be given off. So if that happens, that one's going to bubble some. All right, number 3, sodium phosphate and copper 2 sulfate. All right, sodium phosphate is Na3PO4. And since it's a sodium salt, I'm going to say aqueous. And what was my other species? Copper 2 sulfate. Copper 2 sulfate. Most of our sulfates are soluble. That's not one of our exceptions, so AQ. All right. 2 ionic compounds. I'm expecting a double displacement. So NaSO4, sodium sulfate. Should be aqueous because all sodium salts are. And then copper ends up with phosphate. Now, technically, this copper was 2, so it should still be copper 2 here. So copper 2 phosphate, I'll end up putting a 2, no, there'll be a 3 there, because phosphate is a -3. So, turn that back to a pen. Cu3, PO4, 2. All right, balancing wise, 3 copper, so 3 copper sulfates gives me 3 sodium sulfates, which gives me the 3 sodiums. Wait, I got something wrong here, because I've there's a 2 right there, because Na plus and SO4 2 minus gives me 6 sodiums, so I need 2 of these, which gives me the 2 phosphates. Now we're balanced. All right, but this one's kind of interesting. This guy right here doesn't fit any of our solubility rules. So right now, we have no idea if that's going to be a solid or aqueous. We'll have to wait and see if it forms precipitate. Now, if it's aqueous, it's going to look like we're just mixing two solutions together, and you still have just look like two solutions mixed together. So if you ever have that in a lab, you're going to want to actually check the temperature, see if it gets hot or cold, because it could still be exothermic or endothermic, even though it looks like nothing happens. It looks like water mixes with water. So that will be an interesting one in the lab to see what happens. All right, number 4, copper metal with silver nitrate. Copper metal with AgNO3 aqueous. All right, it does fit the picture of a single displacement reaction. So if something happens, the copper is going to replace the nitrate or the silver. Copper typically forms a positive 2 ion. So that's what I'm going to actually draw it as making. And that should produce silver coming off. Nitrates are always aqueous. This is a metal by itself, so it's a solid. The only one that's not is mercury. It comes off as a liquid, but we'll never do that in our lab. All right, so if this happens, this is going to be a pretty neat thing. You'll have a solid piece of copper, and over time, it won't be super fast. It's not like it's going to happen immediately. We should see it cloud up and turn silverish color. Now, the silver might look kind of brown depending on how it forms, but we are going to see a definite precipitate forming on the top of the copper. It's going to be little flaky pieces of metal. And if we let it go long enough, this copper nitrate will actually have a blue color in the solution. So the solution will slowly turn blue. But the blue solution might not be as obvious in the time constraints of a lab, but we will definitely see the solid if that goes forward. Now, if nothing happens, if it just looks like the copper got metal, then if it looks like the copper got wet, this is one of these that would prefer to go backwards. So, and that's a possibility. So there's no guarantee a single replacement reaction goes forward. All right, number 5, hydrochloric acid and sodium bicarbonate. All right, this is 5th grade science fair project. Any acid with baking soda causes the baking soda to break down. Baking soda will dissolve completely because it's got sodium with it. But when it breaks down, I'm going to draw out something and then I'm going to change it here. The sodium does end up with the chlorine, and you do just get salt. And it will dissolve in water in this case. The H ends up with the HCO3, and we could write H2CO3, and it would be aqueous. That is actually carbonic acid. That's what the name of it would be. But it turns out carbonic acid will actually fall apart on its own. That is actually better to write always as H2O, as in plain old water, and then CO2 gas. Turns out sodas like Pepsi and Coke, you used to see on the label carbonic acid. But everybody worries about that name acid, so they started calling carbonic acid carbonated water. Turns out they're the exact same thing. So this is a neat one. When we mix any acid with baking soda, the baking soda, the carbonate part, breaks down into carbon dioxide. So it bubbles. All right, number 6, aqueous nickel nitrate and aqueous sodium hydroxide. It's nickel 2 nitrate. So it's NiNO3 2. And all nitrates expected to be aqueous. And nickel nitrate and sodium hydroxide, NaOH, aqueous. And we're just doing a double displacement. So I'm going to put the sodium with the nitrate and make sodium nitrate, which I predict to be aqueous because all sodium salts are. And then the nickel ends up with the hydroxide. It'll still be nickel 2, so that is NiOH2. because that 2, I'll need to put a 2 here, which puts a 2 there. All right, but nickel hydroxide, we can make a prediction on solubility here. It's a hydroxide. It's not a group 1. It's not any of those exceptions that are soluble. So this one is predicted to be solid. We should see a precipitate of nickel hydroxide. All right, number 7, copper metal and zinc nitrate. Copper metal and zinc nitrate. All right, we were paying attention to what we said on 4, and we said, well, that's what happens. It does that replacement if it goes forward. We actually can't safely make the call always, so it'd be okay if we went into the lab and had this as blank, because we might end up saying no reaction. We might even have to come up here and say no reaction. But right now, we're I'm just going to go ahead and predict what it would do if it does do a double displacement or a single displacement. So I'm going to have zinc come out as a solid and the copper end up with the nitrate. And it would be aqueous because nitrates are. And we'll find out in the lab if it is. We're going to get a chance to see it. All right, number 8, hydrochloric acid and sodium hydroxide. In class, this was the example equation we went to with neutralization reactions. So anything that is an acid has an H out in front, and any of our bases with an OH on them, if we put those together, it's a neutralization. The H and OH make water, and then the other 2 components make a ionic salt, in this case NaCl. And being a neutralization, we're perfectly expecting that. Now, all neutralizations, doesn't matter what acid it is and what base it is, they're either going to be exothermic or endothermic, and most of the time you can tell the difference. Now, you'll be watching the results. You won't get a chance to feel the test tubes. I'm going to be actually using a temperature gauge so you can see that. All right, number 9, aqueous sodium chloride and aqueous potassium nitrate. Aqueous sodium chloride. I don't know why I'm doing a L. And potassium nitrate. Potassium nitrate, KNO3. All right, this is interesting. Sodium and potassium are group 1s. So even when I do that double displacement, put the K with the Cl, I would still expect aqueous because it's potassium. And the Na with the NO3, I'd still expect aqueous because it's sodium. I'm actually not expecting to see this to do anything at all. Looks like a sample of water and a sample of water get mixed together. All right, so when we do this one, we're going to measure the temperature because maybe there is something going on that we can see thermally. It might just be mixing water with water, but we're going to actually check it because that's one that on paper looks like it does absolutely nothing. All right, number 10, magnesium metal and sulfuric acid. All right. This is actually kind of similar to what we have up at the top with number 2. It's an acid with a zinc. We are actually expecting a single replacement reaction. So the Mg should end up with the sulfates, and then the hydrogen should come off as a gas. Now, that is the single replacement reaction we're expecting with almost any gas or any metal and acid. Now, it turns out, just like 2, we're going to find that some metals don't do anything at all with acid, which is kind of a good thing because you might need to store the acid sometime. And if you can't store it in metal, it's kind of scary. Matter of fact, a metal that's very restrictive on working with acids is actually gold. There's no one acid that will really do a good job of getting gold to go through this reaction. But we're going to find out if zinc or magnesium does. Matter of fact, we might predict that both of these will, simply because if I back up here to the activity series, zinc and magnesium are up on the highest activity. Highest activity implying that they should react fast. And there's our gold down at the bottom along with silver, which are low activity. And I just said that gold doesn't really react with acid too well. All right, number 11, our last one. It is aqueous iron 3 chloride. Iron 3 chloride would be FeCl3 aqueous. And we're going to react that with ammonium hydroxide, which is NH4OH. It's also aqueous. All right, it's just a single replace, or it's a double displacement. So I'm going to put the ammonium with the chloride and make Na. Ooh, I drew that as a. That is not. That should be an arrow. So I'm going to put the NH4 with the chloride and make ammonium chloride. I expect that to be aqueous because all chlorides are, and most chlorides are, but all ammoniums are aqueous. And then I'll put the iron 3 with the OH. And hydroxides, there's very few of those that are soluble, so I'm predicting this to be a solid. And I'll balance this by adding a 3 in front of that and a 3 in front of that. All right, so that should form a precipitate. All right, so we have a prediction for our reactions, and when we get to lab, we're going to see how well that compares. And I won't actually be showing this data sheet in the lab because I actually am going to just set up with a camera that should focus mostly so you can see the actual reactions. I'll be holding them up and then I'll write it down later rather than cutting back and forth. So I will actually have this data sheet done again, and it's going to be what I do in the lab, and I'll have it written out with some more details, and I'll have that posted on with these videos.